We're going to look at how we connect rotations to circular motion and how we kind of switch back and forth. So let's jump on in. So the general idea is I want you to start by imagining a disk with a dot on it. So I'll draw it up here. So I've got a disk, a CD, a frisbee, whatever you can think of, a plate. And if I draw a little X on here instead of a dot, just because I've only got one color, if this spins around in a circle like this, you're going to imagine that this X is going to eventually move in a circle, right? It's going to go all the way around and end up back where it started. So as the disk spins, the dot moves in a circle. So there's some sort of relationship between rotation and circular motion, right? If this moves in a circle and the disk that it's sitting on is spinning, like they've got to be connected in some way. So we're going to jump into that. The first thing that we need to talk about is arc length. And arc length measures the distance between 2 points on a curve. So if I imagine my circular path, so imagine we've got a path that we're going on a circle, and I've got a point here, A, and a point B, say over here. Then the distance, like if I lay a string, let me swap to a different color. Let's go with red. The length of this curve right here is the arc length. So it's not a straight line between A and B, it's along the curve here. So you can imagine if you wanted to measure that, you could lay out a string and then stretch it out and measure that. Or you could get a tape measure that bends and stretch it around. But if we use this example of a circle, the arc length equation becomes nice and easy. It's that the S for the arc length is equal to r theta. So S is arc length. R is the radius of the circle. So this only works for circles. And also, this is the angle measured in radians. So we do have to use radians. So if I go up here and draw in these labels, we'll see that this is the distance r, this is also the distance r, and this angle right here is my theta. And this distance in red up here is my arc length s. So if I have this length s, I have the measurement in theta, I can find r, or any other combination of this. This is seen clearly with a full rotation. If you go all the way around, theta will equal 2 pi. So then I have S equals R times 2 pi, which you'll hopefully recognize as 2 pi r is the circumference of a circle. And what is the circumference of a circle? It's the distance around the outside edge. So we see that this, this matches up, this works out. And this also can be used for changes. So it doesn't have to just be S, so I can use this idea of change in arc length equals change in theta times r. And just as a side note, if you're interested, this is where we get our definition for radians. The radian is the angle where S is equal to r. So if you, imagine any circle and you draw an arc length that's exactly equal to the radius, then that angle will always be the same, and we call that 1 radian. And so that's why when we go to pi radians, we get the full circumference of the circle being the same there. So now that we've talked about kind of how to relate positions, right? Position around the outside or distance traveled around the outside to the rotation, the theta, now we can do the same thing with the other quantities, angular velocity, angular acceleration. So if we divide the change in arc length by the change in time, it'll change to angular velocity. So if that wasn't quite clear, we start with delta S equals R delta theta, and then I'm divide both sides by delta t, so delta S over delta t is equal to R times delta theta over delta t, or in other words, this is equal to V, or average velocity. Well, technically this is an average velocity, but for reasons that I'm going to skip past, it's also the same as the velocity, or we can use an extended logic to find the velocity. V is equal to R omega. So again, S is just a distance, and a distance divided by a time will give me functionally a velocity. Delta theta over delta t, that's just an angle divided by change in time. This goes back to where we defined omega. And so we have this relationship here, that V is equal to R omega. V is defined as the tangential or linear velocity. Both phrases are used and they mean the same thing. So I'm just telling you both because I use them interchangeably as a habit. So this velocity is essentially the same as the v, the speed in the circular motion equation. So the tangential velocity is basically how fast the object is moving if you like cut the string or let it go just in a straight line, or if you take the total distance it travels around the circle and divide by how long it took to travel around the circle, this is that v that we're looking at. Now if we relate the angular acceleration, similarly for acceleration, by the same logic we can divide the previous equation by delta t, and we'll get the idea that a is equal to r times alpha, where alpha is the angular acceleration. But a is not the same as centripetal acceleration. So the linear or the tangential acceleration, which is what we're talking about now, just plain a, this one right here, describes how fast the speed changes. Centripetal acceleration describes how fast the direction changes. And this is only for circular motion. If you don't have circular motion, it gets a little weird. But centripetal acceleration is basically, because it's always pointed towards the center, it's never going to change the speed. And tangential or linear is always pointed in the same direction, so it will only change speed. The distinction here isn't super important. It's not going to be something we spend a lot of time on, but I do want to point out that they are different, and if you want to talk more about it, check in with me in class. So what's the implication of this, or like why do we care about kind of the two things? How are they related? So multiple objects can have the same angular velocity, meaning rotational speed, but different linear speeds or different tangential speeds. So for example, if you have a disk like this, and if I have a point here and a point here, we'll call that A and call that B, they both have to go around a complete revolution or rotation at the same time, right? A can't go faster than B if they're both stuck to this disk, because otherwise then the disk would shred apart and fly into pieces. So they have the same angular velocity. But points farther from the center have a larger physical distance to cover, right? The path, right, 2 pi r for B is bigger than 2 pi r for A. Like B travels a farther distance, so it has to have a larger linear velocity. So this is where it gets a little interesting, maybe a little weird with kind of rotations, is multiple objects can have the same angular velocity or angular acceleration, but the farther you are from whatever you're rotating around or traveling around, you're going to have larger or smaller linear velocities or accelerations again. So that's what we're looking at here. Let me know if you have any questions.